Our temples, stepwells, and forts were not just built, they were understood. To explore how ancient tradition, ancient wisdom, and modern engineering can work together, we welcome Dr. Arun Menon, Professor, Structural Engineering Laboratory at the Civil Engineering Department, IIT Madras.
Namaskaram. Very good afternoon to everybody. Sorry for that little technical glitch in the beginning. I was expecting, and so I had multiple options, and sometimes you run out of options. At the outset, I'm extremely grateful and humbled to be here to talk to you about our experiences of technology and culture, where technology and culture meet. The examples that I thought I should talk about today, demonstrating that linkage between the traditional knowledge systems and the modern knowledge systems, is really a work of multiple people, work that has happened in the last decade and a half and more at IIT Madras in the Civil Engineering Department. I have had the pleasure and the opportunity of working and guiding some of these works, and many of these are with other organizations and other entities, other agencies in the country. And so these have been extremely important avenues for us to start working in this field and learn more about this very less discovered subject of traditional Indian architecture, at least from the modern lens, because most of our modern engineering and architectural education is rather oblivious to the details, the approach adopted in the ancient India. So I have tried to pick up 4 examples, and in the next half an hour or so, I would really want to go through these 4 examples. They have there are different reasons why I've picked them up. And I hope you will see the difficulty that we've gone through. You have to do a lot of unlearning and then learning, because as I said, most of us have not been exposed to the traditional knowledge systems, but then start discovering that you have such a rich parallel system of knowledge that existed and exists in this country. And a lot of effort is essential from our side to reach out and try and understand what this really means and how it operates, and how today a convergence between the modern knowledge systems and the traditional knowledge systems can be achieved. And in our efforts to preserve culture and the heritage of our country, unless we make a conscious attempt to bridge this divide, I think it will continue to survive, survive as parallel systems of knowledge, but the synergy of bringing these two together is something we'll completely lose out on. So that's been at the bedrock of our inquiry. So let me, without further ado, go into these examples. Please, next slide, please. So, Civil Engineering Department is where I come from. I did my bachelor's in architecture, and my training has been in earthquake engineering. My training has been in natural disasters, and so we are taught to work towards disaster risk reduction. What can be done for disaster risk reduction in the civil infrastructure? Because we are taught and we realize that natural disasters don't kill. Often it is the buildings that kill in natural disaster, or even in a human-made disaster. So if you take up a country like like India, we already face a lot of natural disasters, not only India, rest of the world, and the developing world and the underdeveloped world really faces the brunt of natural disasters. If you take natural disasters and historical constructions, built heritage, we can actually see that it's the natural heritage, the built heritage is really has an augmented vulnerability because of the age of the infrastructure that we're talking about. The Bhuj earthquake, 25 years now, in January 2026, this January, we had a commemorating event. It's 25 years since that landmark event. In fact, it's a landmark event for many reasons in engineering because it led to a sudden change in the direction of the structural design codes. So the 26th January 2001 Bhuj earthquake, in terms of its impact on historical constructions and heritage, built heritage, Kutch alone, the Kutch district alone, had about 15,000 heritage properties, of which 10,000 of them, two-thirds, in less than 80 seconds, that's the length of the earthquake shaking during the Bhuj earthquake, was wiped out, completely destroyed, and some beyond repair. Well, natural disasters will not stop there. After 2001, we've had the Indian Ocean tsunami, the Kashmir earthquake of 2005, the Sikkim earthquake of 2011, Kedarnath floods of 2013, Kashmir floods, the Nepal earthquake of 2015, Myanmar earthquake of 2016, and almost 10 years later, the same region in Myanmar was affected by the massive Mandalay earthquake last year. So this is what it's going to be. And while there is definitely loss of human life, loss of infrastructure, there is a silent death that cultural heritage is also facing. And in many cases, cultural heritage is an important element of the economy of a country. Nepal, for example, was brought to its knees in 2015 when the Nepal earthquake happened. So it's interlinked to history, the culture, and economy. So there is a need to look at historical constructions and understand their vulnerability to natural disasters and see in today's modern era of technology what can be done to mitigate the effects of future natural disasters. And that's where our interest comes in. Can we study these ancient constructions? Can we see if they will survive in a future natural disaster? And what interventions need to be carried out to ensure that they survive and the loss of history and loss of economy due to the loss of such elements of our past can be avoided. Next slide, please. In fact, in 2001, the earthquake zoning map of the country was changed. 25 years later, today, we have adopted a new zoning. This is the earthquake zoning, and we can talk about cyclone zoning, we can talk about landslide zoning, we can talk about multiple natural disasters and human-made disasters. In fact, the reason for showing you this map is if you look at the earthquake hazard map of our country, today we have 36 cultural heritage sites in the country. And of these 36 cultural heritage sites, almost 60% sits in moderate to high earthquake zones. And in fact, if you go to the latest map, the one on the right side is the latest map, some of these high earthquake zones have been reclassified into very high earthquake zones. So the danger is present, and it's important that we act on it towards disaster risk reduction. Next slide, please. So the first example that I'm taking up is we have seen mandapas, and mandapas are present all over the world, all over the country, in different forms and different materials. In South India, in a state like Tamil Nadu, there are hundreds of them, thousands of them. Next slide, please. We started looking at, right from the Bhuj earthquake in 2001, we've seen number of these mandapas don't survive the earthquake. And in Gujarat, in Bhuj, in Nepal, we have seen complete collapse of these mandapas. 4-pillared, 16-pillared, multiple pillared. Anything above 50-pillared in Dravidian architecture, we tend to call it Ayramkal Mandapam. So these constructions have collapsed in the past earthquakes in, at least in central India and northern India. Next slide. Next, please keep clicking. So that's in Bhuj. You can see a beautiful chhatri with domes from constructed sometime in the 1800s and then completely lost in the 2001 earthquake. Next. That's in 2015 in Nepal. A beautiful stone construction. And what you can notice is at the bottom, there is a tenon and mortise joint. There is a joint between the stone pillar and the base. And this implies that there is some understanding that there should be lateral resistance when there is an earthquake, and this is an interlocking that's available. But sometimes the earthquake shaking is so severe that even that does not allow the structure to survive. And we've seen the structure collapsing because of the shaking. And this was observed in 1934, the great Indian Bihar-Nepal earthquake, and repeat in 2015. Next. So the big question that comes up to our mind is, okay, these seem to be vulnerable structural systems. What would happen if in a region like peninsular India, we have a moderate earthquake? In South India, can anybody here, of course, none of you may be working in the subject of earthquakes. Can you tell me what is possibly the largest recorded earthquake in South India? That occurred in South India, not that occurred in Bhuj or the tsunami, the earthquake that generated the tsunami, and we felt it here in Chennai. But something that occurred in South India, the largest. I didn't know this, and I only when I started looking at earthquake records did I come across this. A magnitude 6 earthquake in 1900 in Coimbatore is the largest earthquake in peninsular India. Now, a magnitude 6 earthquake, and if you're near the magnitude 6 earthquake epicenter, it's enough to pull down structures. Okay, so, and there is recorded damage in Ooty and Coimbatore and that region in the 1900 earthquake. So our question was, if there is an event comparable to that, what would be the possibility of survival of these vulnerable constructions in South Indian temples, the mandapas? And the reason for the inquiry is when you look at the North Indian mandapas, you do see the tenon and mortise joint, the interlocking, which does provide some amount of basal protection to the structure from lateral loads. South Indian mandapas, if you actually look at how the design and execution happens, these do not have interlocking at all. These are literally flat, or at the most, there's a slight curvature, granite beam to the granite shaft, and that's only to ensure alignment. It is not to create interlocking, which means there is nothing that is actually tying the beam to the columns. So where do we stand in terms of vulnerability? In 500 years, we've had one earthquake, magnitude 6. In 1,000 years, we don't know. In the next 500 years, we don't know. Do we want to preserve these structures for eternity, for as many years as possible, as many centuries as possible? Yes. Are we well prepared to do that? So that was the inquiry. Next. And so we did some basic calculations. Engineers are always interested in number crunching, and we did some number crunching based on some information that we had. And we realized if you look at these South Indian mandapas, problem. They do not have the necessary factor of safety, even if you look at the structural design level of earthquake shaking that is prescribed by the standards. So what do? We were not very sure if this conclusion that we had arrived at is correct. So engineers always like to validate it. So how did we validate it? Next slide, please. We decided we need to look at a full-scale model. Let us construct a full-scale model in our laboratory next. And in doing this, we said, okay, we don't know how these are constructed. We need to bring a sthapati in we worked with a stapati, and this is stapati, stapati who's been working in Tamil Nadu for decades, stapati Kumaraguru Baran, and he worked with us in dimensioning, choosing the material, and finally constructing it and giving it to us. And we constructed this. Next, please. We constructed this. We have at IIT Madras, I don't know if some of you have had the possibility of visiting IIT Madras. When we conduct the open house, we've been conducting the open house in early January every year now for the last 3 years. And in the open house, we keep all our laboratories open. And we've been actually showcasing this laboratory as well. We have what's called an earthquake simulator, a shake table facility. And this shake table facility is something that is power-driven. It is driven with hydraulic power. And we can actually build a structure on top of this table and simulate an earthquake. So what did we do? We got this stapati to work with us, build us mandapam, exactly how the mandapam would be built in traditional Hindu architecture, and placed it on top of the shake table and tested it. And there is a protocol in terms of how this testing is done, and we identify at what level of the shaking does the structure collapse. Now, that's seeing is believing, and then we go back to number crunching, correct our models, and then see if we have now a good analytical understanding of what's the capacity of these structures. And that was the whole intent. Next, please. So we did that. We ran these earthquake. You can generate a real earthquake on these tables, and we did that. We keep increasing its intensity till it collapses. So we do it in a very systematic manner and record it. We put sensors on the structure. It then tells you how the structure is responding to the ground shaking that is happening. Next, please. So that's the mandapa on the shake table for you. And it's sad to see structures collapse, but engineers take pleasure in seeing structures collapse, and that's simply because you learn something out of it. You can call it sadistic pleasure, but it, when there's an earthquake, engineers scramble to reach the site of the earthquake simply because that's an opportunity to see how structures have performed, and that informs codes, that informs education. So we have funny people. So if you can click on the right figure, it will play. If you can just click on that last big picture. Yes. Yes. So that's now, the table has now started shaking. It's not the screen, it is the table that is shaking. And our intent was to take it to collapse, and then we did that. So we did that. Next slide, please. As I said, yes, the experiment functioned, but as engineers, we should be able to explain the mathematics behind it. So we do what's called numerical modeling. Next. We try to create a computer model and give it properties of the actual structure, and then try to see if it's behaving really the way that the experiment behaved. So the experiment is the validation of anything that is simulated. So this is the simulation. Next, please. And we also said, okay, all this hi-fi computerized simulation, it's like a black box. Sometimes it works, sometimes it doesn't work. Can we do it by hand? And we did it by hand, and we were able to get the same numbers. So using highly computational models, and by using simplified hand calculations, we were able to replicate the behavior of the mandapa as observed in the experiment. And that gave us a lot of confidence in terms of our understanding of how these systems work. So what's very interesting is exactly how the structure failed. When it was overturning, it had two joints opening up, and exactly at the locations where these joints opened up, the mathematical model also was able to come up with the same prediction at the same level of the earthquake. So that gave us confidence. That was like the proof of the pudding, and we said, okay, good. Next, please. So we did that, and this was an interesting project. You can go to the next. So this was an interesting project where what we did discover is the level at which these South Indian constructions, the mandapas conceived in South India without any connection, which is what the sthapatis have been used to in constructing for hundreds of years, are stable enough for the level of shaking that occurs in peninsular India, right? However, they are not definitely sufficient when they occur in other parts of the country, like the Andamans or Gujarat or the Indo-Gangetic plains, Nepal, and so on. So the learning from this was, well, for the kind of constructions that we have in peninsular India, they appear to have sufficient factor of safety against earthquakes. But if you go to moderate to higher seismic zones, we understand what can cause their collapse and hence what might be required to retrofit them so that we don't lose these constructions in these earthquakes. So one interesting aspect I think is worth speaking about as we were doing this. When we construct a model on the shake table, we subject the table to the vibration, and engineers are comfortable when we bolt the structure onto the table. Otherwise, when you're doing this test, the structure might fly away from the table. And so we wanted to actually fix the mandapam onto the table. The sthapati was very clear. You want to do that, I am not going to build this for you, because that is not how the traditional construction is. And he wanted a pit of about 6 to 8 inches of sand to be placed, and on this, the mandapam would be constructed. So we had to create a small container, fill it with sand, and then the stone structure was to be constructed on top of it. Now I really didn't appreciate why you needed 6 inches of sand or 8 inches of sand on which you want to construct a structure. I said our table is 100% flat. You can be quite confident you'll get verticality, you will get plumpness, and you can construct. He was not convinced. And it was when the sthapati started constructing that we realized the importance of the sand in the traditional construction system, the way all these temples have been constructed. And when each layer is placed, after the first layer is placed, the verticality is checked. It's very difficult to cut stone perfectly. The big blocks of stone may weigh more than a ton, and so cutting them perfectly is a skill. But human error can be there. And so a flat surface may not be a flat surface. And therefore, when the second layer is being placed, if it's not flat, then simple tapping is done, and the sand will accommodate. And so layer by layer, as this is being placed, verticality is ensured because the sand is helping you accommodate that. Now, if we had constructed it on a rigid foundation, rigid reinforced concrete foundation, or said rigid steel table and nothing more for you, he would have not been able to construct something that is geometrically as perfect as possible, as perfectly aligned as possible. So I think it was also an exercise for us to appreciate the traditional knowledge approach in how this is constructed. And I think if we had overruled him, we would have got dramatic results which were not true, and vice versa. Let me move forward. All of you, many of you, may be having this type of a flooring system in your homes. It's called the Madras terrace construction, right? Madras terrace construction gets its name because it was popular in the Madras presidency, but from 1600s and 1700s, this is quite popular in peninsular India. And some of you may know or may not know that this is actually sitting in the Bureau of Indian Standards, and there is a Bureau of Indian Standards dedicated to Madras terrace construction, and it will tell you exactly how many rafters must you place, at what angle must you keep the bricks, and what composition of the lime must you use, and so on. So we were interested in studying the Madras terrace construction because we end up looking at many historical constructions where the Madras terrace slab is almost collapsing or in very bad condition because the timber is deteriorating and needs to be replaced. And very often, what are we doing when we want to replace it? It's very difficult to get this constructed. People don't know how to repair this. And the skill to do this is not available as much as it was a few decades ago, and therefore replace this with reinforced concrete. And in the process, we tend to lose a very good system that is efficient from construction point of view, thermally efficient, and structurally efficient or not, it was a question in our mind. And particularly, next slide please, particularly what was happening is, in many historical constructions, particularly from the colonial period, Many of these buildings have Madras terrace constructions which are damaged, and a simple statement that the structural system has outlived its life is sufficient to pass the death sentence for these buildings and demolish these constructions. So we really wanted to understand, is there any possibility of repairing these, particularly when a place like Madras, Chennai, is now in seismic zone 3. From 2001, it's been in earthquake zone 3. Public buildings have to be checked for earthquake safety. And this typology of construction was not getting classified as safe under earthquake loading. So there was a risk of classifying this as an unsafe construction simply because we have not been able to understand how this really behaves under earthquakes. So what did we do? We picked up this construction. We again had to work with the sthapati, because if you call a modern engineer and an architect and ask them to build Madras terrace construction, we can only get pictures. We can't get a Madras terrace construction done for you. So we worked with the sthapati from Auroville, from Pondicherry, and he built us a very nice Madras terrace floor slab in the laboratory. This is structural engineering laboratory in IIT Madras. And we wanted to subject this to lateral loads. And when we subjected this to lateral loading, like in an earthquake, we realized what was happening. The timber rafters would move independent with respect to the brick and lime concrete overlay. The brick would simply slide. But if some of you have actually got some repairs to your Madras terrace done, you will realize that a mason can come and change a single rafter and replace it with a fresh piece of rafter if the old timber rafter is damaged without affecting the entire slab. So there is an ingenuity in the way the whole thing is conceived. But that was also the problem for it when it was subjected to lateral forces. So when you subjected the slab to lateral forces, it would all not work together. There was no integral action. So next. So then we decided, can we, instead of replacing all these with concrete, can we suggest something that's quite simple? And we worked out that by introducing a small anchor, a small hilty anchor that integrates the timber rafter to the brick and the lime concrete overlay, and deciding how many are required in the entire Madras terrace slab, we were able to see that the lateral load performance was phenomenal, right? So with a very simple intervention, it was possible to make this seismically retrofitted and adequate for the level of earthquake shaking that is expected in South India. So it is possible to declare that this is safe as long as there's no deterioration of the material. With little bit of intervention, you can retain the structural system, which is the traditional structural system and an identity of the region. So next. So this was really, again, needed an understanding of how traditional construction systems are done. What's the rationale behind it? Is there a lacuna? Is there a gap that we can address through engineering and then ensure that the synergy gives you a solution that helps in preserving the history? So this was the second example. Let me move on. Third one. Third one is a beautiful temple. The last two examples are temples. This is, anybody here seeing this unfinished Gopuram? Not Marundishwara, Tiruvellarai. And I think I've spoken enough in the last few years about this, and probably that's where this is. Sri Pundarikaksha Perumal temple in Tiruvellarai. Tiruvellarai is about 2 kilometers from Samayapuram, and it's governed by the Srirangam temple under HRNC, under the Hindu Religious and Charitable Endowments. So the story here is the Gopuram. Next slide, please. The Gopuram here, again, a structural system that we don't learn in textbooks in civil engineering and architecture. Like the mandapam, we don't study that in civil engineering. Wherever you go, you see mandapas, but it never exists in our civil engineering and architecture curriculum, not even school textbooks. So this is a story of an incomplete Rajagopuram, the main Gopuram of the temple. And what is existing, you have one stone layer and 2 brick levels. And of course, there is an intention to complete this, simply because we are looking at a structure that is incomplete within the temple. And that's not considered auspicious, that's not considered, the composition is not complete. And the temple is considered to be the body of God, and you want all parts to be in good condition. Jeernodharna also requires that you refurbish and you complete things. So the whole idea was here, the local community, the priests, the religious order there wanted to ensure, wanted to check if this can be completed. But we're talking of a structure that was constructed in between 1300s and 1400s. So about 700 to 800 years ago that this was constructed. So then, before the HRNC, Hindu Religious and Charitable Endowments, said we can approve the construction of the Gopuram, completion of the Gopuram on a historical structure, we want some institute to study it, civil engineering institute to study it, and say it is safe to construct it. And there is also a reason why they wanted that to happen. In the 1940s or 50s, there was an attempt to start construction, and they were removing the floor slab and they were putting in a reinforced concrete slab, and there was a collapse. There was a partial collapse, and there was casualty. And so there is sensitivity in terms of heavy structural work that can lead to loss of life if things are not planned well. And that sensitivity on the part of the government institutions is well accepted. So we started our investigations here. Again, a structure that we don't know much about, and we really have to start digging to understand what it is. So we did some structural investigations. We today use non-destructive testing, very much like you go to a doctor and the doctor runs all tests on you. We extract some samples from the structure. We do some imaging. So there are different things that can be done. We wanted to understand where is the foundation, how deep is the foundation, what is it founded on, the strata, how good is the brick part, how good is the stone part of the structure, and so on. So you can see these pictures give you an idea of that. Next slide, please. We also had no clue, these constructions are massive. On the ground floor, the wall is about 5.5, 6 meters. If you have gone to the Srirangam Rajagopuram, if you've gone to the Srirangam temple, the Srirangam Rajagopuram, the wall on the ground floor is 12 meters thick. Well, it all looks nice from the outside, it's stone, but what's the story in the cross-section? And that's what structural engineers want to know about, because the strength is coming from that. So we actually had to drill through and get a core sample and understand what the cross-section is. So we did that. This is core drilling. Next, please. And then we had a conjecture of how the Kalkaram of the Gopuram is constructed. And then we were a little more confident. Yeah, now I know it's not full granite. There's part granite, and then there is part filling material. And so that information is useful. Please go forward. And then, as I said, numbers, number crunching. We do some calculations. We do some models. You can keep pressing. So we then looked at existing structure, plus the 5 stories that have to be added. How is the structure going to respond? Is it safe? Is it, from a structural engineering design perspective, is it acceptable? So we did that. That's what you see in these pictures. Next, please. And then, again, as I said, today's requirement is not only under gravity loads, as under lateral loads as well. So we have to do checks under lateral effects, earthquake effects, and wind effects. So we did that. And we found that it is feasible to go ahead with the construction of the missing stories. Of course, this is documented, and this was submitted to the HRNC. But this structural engineering input is only one input. The feasibility to construct is there. But then the archaeological perspective has to be taken. Next, please. And as I said, the reason why we are sensitive about this is even in this temple, when some work was being done in the 1940s or 50s, there was some collapse. In 2010, some of you may remember, in Sri Kalahasti, the Vijaya Gopuram in Sri Kalahasti collapsed with a little warning, one fine morning. And so these structures, unless we understand them well, they might have problems, and non-engineered approaches can backfire. So that's the whole reason why this had to be done. Next, please. The sthapati, looking at the dimensions of the original construction, has been able to arrive at what would have been the original prescription for the 7-tiered Rajagopuram. The conjecture was put down on drawings, approved through engineering checks, and today, next slide please, the construction is, so as I said, you needed an input. This is highly multidisciplinary, and this is where traditional knowledge and modern knowledge needs to come together. Next, historian. You need the archaeologist, you need the agama expert, the traditional sthapati. You need science and engineering through non-destructive testing, structural assessment, analysis. And then finally, to execute all this, you also need project management. Because it's a whole lot of material, whole lot of things that you don't use today. You have to procure timber that is so large in sections. There is a project management challenge as well. And finally, this is now commencement of the construction started in 2018 by repairing the original structure. The original structure had undergone some damage, and some repairs had to be done. And this is last year, sometime in the middle of last year. Now we are at the 5th story, and hopefully in the next few, in 2027, it is expected to be completed, and some prokshanam is supposed to be carried out. Next slide, please. Last project, and you know, it is lovely because hundreds of people have to come together for this to happen. And maybe 99 have come together, nothing moves. And then one more has to come in, and then things start moving. So all these, the work at Pundrika Perumal Temple started in 2014, the initial thought process. The first brick could be kept there only in 2022. So it takes a whole lot of time, energy, and patience, and confluence of all these knowledge systems to make a difference. This is the last one, and this is, I'll close with this, I'm overshooting my time. This is again a conservation project where temple restoration is being done, but what was a big takeaway for us at IIT Madras was the subject of Ayadi Ganitam, which goes into how, I mean, the science behind how the dimensioning of the temple is done. And we, I mean, in 45 years before I started working on this, I never knew something like this existed. And that's the strange world we live in, right? This, in up to 2020, the picture of the Rajagopuram, some of you must have visited this beautiful temple. It's Sri Abatsahayeshwarar temple in Tukkachi village in Kumbakonam district. It's a beautiful temple. That was how the Rajagopuram was for several decades. Well, happy to tell you that in 2023, this has been completed. And again, I think thousands of stars had to be aligned for this to actually happen. So many people were involved. So many systems had to fall into place. Next, please. In 2017, when we started working on this, we said there was a crisis in HRNC department, and there was a ban on any conservation work in temples in Tamil Nadu because there was a high court case that was going on. And as many of us were involved in a court-appointed committee in helping the temples department move forward on in the interim period, move forward on conservation of all these temples. See, the HRNC department, as many of you may be knowing, has about 42,000 temples, of which 9,000 temples are historical temples. Now, when there was a blanket ban on any conservation work till the case was completed, the problem was Kumbhabhishekams have to go on in many temples. Some of these temples have serious structural issues. Can you just sit back and wait for the case to get over? Cases take decades to finish. So in the process, the court appointed an interim committee, and the interim committee was examining things, and it was suggested by the interim committee that why don't we pick up a pilot temple, pilot case study, and then work with the HRNC department to ensure its restoration. So that is how we picked up the Tukkachi temple, Abatsayeshwara temple, and IIT Madras from 2018 brought an MOU together, started putting things together, and we signed the MOU on Shivaratri of 2020. But all of you know what happened after Shivaratri of 2020. March, lo and behold, was the pandemic. And with the signing of the MOU, we couldn't do anything else. We couldn't even step out of Chennai, forget reaching Kumbakonam. So till July, August to September, we were not even able to go back to the temple, but we began our work. The blessing in disguise was the place was available with nobody around, and we could work for 3 or 4 months to completely document. Next slide, please. So the temple itself is a very beautiful temple. It was constructed during Rajendra Chola period of Rajendra Chola, and then expanded by Kulothunga Chola and Vikrama Chola. And it's datable to the last phase of the Chola kingdom. Next, please. And Sthala Puranam talks about the whole place being a forest of patri trees. And this has the stream, the stream that is there close to the temple has, the pond that is there close to the temple has medicinal properties in its water. And the legend is that Vikrama Chola was cured from a health condition because of that. And then that's how he promises to build a temple there. Next slide, please. So this is the state in which the temple was, and the temple was like this for about 60 to 70 years. And so you can imagine most of the people living in that village, which goes by the name Tukkachi, which is actually Durgayachi, and the temple of Sri Abhatsayeshwarar has a shrine built almost at the same time for Durga, and hence the village gets its name as Durgayachi. Now, a village where this temple exists, 60, 70 years when the condition of the temple is like this, most people who have not seen the glory days of the temple would associate with disrepair, with darkness, and wouldn't go anywhere near the temple, and that's exactly what we saw. Most of the village was completely disconnected from the temple. Only the elders in the temple had a soft corner, and they always wanted to see this revived. But it's taken so many decades. Please move forward. There's a video. This is available online, and I think I'll take another 2 minutes and close. So this was in very bad shape and had to be moved forward. So the reason for talking about this is when we took up this in Jeernodharna, in Mayamatam, there is a section that says, how do you do Jeernodharna in a temple? And there are 6 stages of damage that you can see. And the last one is about, okay, all the damages can be repaired. If there's a crack, you repair that stone. If there is tilting of a wall, you repair that wall, and so on. The last one is Ayadi. They say, if the Ayadi is incorrect, then you can even, in the Jeernodharna, correct the Ayadi. So that was an interesting point, and we thought when we do a conservation project, it is important to go back and understand the basis with which the construction has been made. And that is where we bring this in. The Ayadi Ganitam is really part of the Vastu Shastra, where the traditional sthapati uses Ayadi to actually, next please, Ayadi to actually proportion the temple. So it is derived from astrological parameters, the directional effects, directional influences of the earth, and one auspicious number is selected. This auspicious number is referred to as the Ayadi, and that is used to proportion the temple. Next, please. This number is believed to ensure, because of the processes that one undergoes to arrive at this number, is believed to ensure the spirituality and durability of the temple, longevity of the temple, if you want. Next, it's the basic unit of dimensioning of a temple, the plan layout, the elevation, the decorative features, everything, all the measurements are dictated by the Ayadi. It serves as a measurement for the length, width, area, perimeter of a structure, sizes of rooms, and all elements calculated using the ratio and proportioning method. So once the Ayadi is arrived at, the Ayadi becomes the perimeter of the Garbhagriha or the Karuvare. Then that is used to see how much should be the first tier height, how much should be the next tier height. And so this number, which is established, which is linked to the presiding deity, or the star corresponding to the village, or the star corresponding to the Karta, the king or the person who's commissioning the work, is linked to the temple's dimensions. So there is a very strong bond between the intent of constructing the temple as a prayer and what is constructed and what is being worshipped in the place. That is a beautiful concept. Let's move forward very quickly. So we tried to understand this from a process of reverse engineering. What we did was we measured the perimeter of the Garbhagriha, the width of the Garbhagriha, and then used that number to try and understand what might have been the Ayadi for this particular temple. And this is complicated for multiple reasons, because today we measure in SI units. or feet and inches. But that was not how our ancient traditional sthapatis were working. So then it goes into a lot of complication. So what is done after the Bhumi Parikshe, when selecting a temple, after the Bhumi Parikshe or Bhumi Sodhane, the site is selected, and then the architectural drawings are made, which is Padavinyasam. And then the Ayadi formula is one number that is selected, and that number goes through a set of mathematical operations, and through those mathematical operations, you get a remainder. That remainder, next please, that remainder may be 1 or 2, 3, 4, 5, 6, 7, 8. Depending on the remainder that you get, the quality of the outcome of the temple, the quality of the constructed can vary. And therefore, you need a good Ayadi. That's where the whole process of trying to get the correct Ayadi for a given site comes up. So each of these remainders may be superior, may be inferior, may talk of poverty, may talk of no longevity, and so on. So that's how the Ayadi has been arrived at. Next, please. So what is this Ayadi? Once this number is arrived at, next, please. Once this Ayadi is arrived at, then this Ayadi number is then measured using something that comes from the rice grain of the land or the human body. So the angulam is used, that's the Manushya Pramana there, and then linkages to the grain of the land. And so the grain of the land, one single grain is considered to be x into 2x. So if you place 8 grains together, you get a superior dimension. But if the grain is not perfectly x by 2x, then you may get only 7, or sometimes you may get only 6. So you have a superior dimension, you have a medium dimension, and you have an inferior dimension. So that's how just the last slide, please. So if you place 8 grains together, then you get 1 angulam, which in today's context would be 1/3 of an inch, or about 3.5 centimeters. That angulam is what is then linked to the Ayadi. So next. So when we measured the perimeter, we then have to look at what is the number of angulams you're getting. And from the angulams, you can get an idea of the Ayadi. And then from the Ayadi, there is the set of 16 or 25 formulae that gives you an idea of how that number has been arrived at. So that's where the reverse engineering is. Please go forward. So in the Abhatsayeshwara temple, we found 4 numbers that were possibly the Ayadi: 29, 31, 729, and 731. And then using what's called the Shodasha Ayadi, 16 calculations that will tell you whether the Ayadi is acceptable for that temple or not. We worked backwards, and we found that out of the 16 calculations, there were 9 good outcomes, 2 fair outcomes, and about 7 bad outcomes on the whole pass. So that number is acceptable. So 29 out of 29, 31, 729, and 731, 29 might have been the Ayadi number. So 29 is the Ayadi number, and that being in the region of Tanjai, the basin, would have been 29 Tanjai Muram. Next slide, please. So that's how, when we looked at 29 Tanjai Muram matches with the perimeter of the Shiva shrine. And that establishes that it possibly was the number which was the basis for the construction. This was finally completed. When we finished all this, and as I said, many things came together. You have to have a donor, you have to have all the sthapatis, and in 2023, September 3rd, the work was completed. Next, please. And this, it was such an interesting time after 60, 70 years to see that there's not 1 inch of place in the temple to stand on that particular day. Frustrated you, but then it made you also happy that there's a transformation to that temple, which is a 12th century temple that is possible. Next, please. And there was a recognition of this. This we thought was interesting, and we submitted this to UNESCO, and UNESCO recognized HRNC for this work. Next slide, and I'm done. I'll close last. Number of people who are involved in this. And just to close, so you can just put all the points there. It comes from structural engineering, modern day structural engineering, engineers. There is a possibility of going back to traditional knowledge systems, trying to link these knowledge systems to the traditional knowledge systems and find convergence. And I think we must attempt that, because unless we are convinced, we are not going to preserve what we have. And as I said, there are parallel systems, knowledge systems in this country. We must take them along. And without them, we can't move forward. And so this was a beautiful way of bringing to life a place, but with everybody on board. And I think that's what we must try and do. I'll close here. I've overshot my time, and thank you very much.
The results of the seismic studies, so at what magnitude do you expect the uninterlocked constructions of the South India to kind of, what's the critical point, the breaking point?
That's a very good question, very important question. But as a teacher, I'll get into teaching mode. The problem is a magnitude is not a good indicator of whether a structure is safe or not. That magnitude 9 earthquake may actually happen in California and nothing will happen to us. But if a magnitude 6 earthquake happens in Coimbatore, we can have some damage. So the magnitude is not a good indicator. We talk of intensity or peak ground shaking. And so what we realized was the peak ground shaking at which we saw the collapse of this construction was actually about 15 to 20% of acceleration due to gravity. 9.8 meter per second square is holding us to the ground. About 20% of that, when applied laterally, can cause collapse of this construction. Now, this can be the basis for us to study much more complex constructions. South India, peninsular India, we don't reach those values in about 500 to 1,500 years. That level of shaking is not expected.
The Ayadi measure you mentioned was connected with the perimeter of the Garbhagriha.
Yes.
So are you referring to the inner diameter or the outer diameter?
Padavargam, which is the part, I would say, central part from outside, outer to outer dimension.
Okay.
As you stand at the first tier, Kalkaram, what we refer to as the Padavargam is the central portion above the Upapedam and all that. And then the outer to outer dimension is that number which then dictates the proportioning. And the Ayadi number is linked to that.
Okay. Thank you.
Thank you.